Hello students, welcome to lecture 1.01. We're going to begin with the idea of Coulomb's force in air or vacuum. If two point charges Q1 and Q2 are separated by a distance r in air or vacuum, then the force is given by the following expression: 1 by 4 pi epsilon naught Q1 Q2 by r squared, where epsilon naught is absolute permittivity and its value is 8.857 into 10 to the power minus 12, and 1 by 4 pi epsilon naught has a value of 9 into 10 to the power 9. It's one of the fundamental forces. It acts along the line joining the point charges, and that's why it's called as a central force. It can be attractive or repulsive depending on the nature of the charges. Let's quickly get into an example. A particle having a charge of 2 microcoulomb and mass 100 grams is fixed on the bottom of a smooth inclined plane of inclination 30 degrees. Where should another particle be having the same mass and charge be placed on the inclined plane such that it remains in equilibrium? A pretty simple problem. Let's get to the solution. This is the diagram. The charge at the bottom of the inclined plane is fixed. Another charge is placed on the inclined plane at a distance r, let's say. Now there is no friction since it is a smooth inclined plane. So for its equilibrium, the forces along the inclined plane must balance each other. That is, mg sin theta should balance the Coulomb force of repulsion between these two charges. So mg sin theta must be equal to k q square by r square, where k is 1 by 4 pi epsilon naught. So solving for r square, we have the following expression. Substituting the values and solving finally, we get r to be 0.26 meters. Another example. Two identical pith balls, each carrying a charge q, are suspended from a common point by strings of length L. If the angular separation between them is 2 theta, which is assumed to be small, at equilibrium, find the mass of either of the pith balls. Let's get into the solution. Here is the diagram. They are suspended from a common point, and equilibrium, let's say they are separated by a distance d from each other, separation 2d from each other. And for equilibrium, at equilibrium, the forces are the tension in the string, the electrostatic force of repulsion between the two charges, and its weight due to gravity. One component of tension, that is T cos theta, should balance mg, and another component T sin theta should balance the Coulomb force. So at equilibrium, T cos theta must be equal to mg, T sin theta must be equal to the Coulomb force, which is k q square by 4d square. Again, k is 1 by 4 pi epsilon naught. On dividing the two expressions and solving, we get tan theta equals k q square by 4 mg d square. But since theta is small, we can assume tan theta to be equal to theta itself. And also from the diagram, sin theta is d by L, which can also be approximated to theta. Substituting and rearranging, we have the mass of each of them to be equal to kq square by 4g theta cube L square, which is the required answer. Moving on to the next idea, Coulomb's force in a medium. So when you have two point charges q1 and q2 separated by a distance r in a medium, then the force is given by 1 by 4 pi epsilon naught epsilon r q1 q2 by r squared. where epsilon naught, epsilon r, the product is epsilon, the relative permittivity of the medium. Epsilon r, which is also denoted by k, is equal to epsilon by epsilon naught. That is the permittivity to absolute permittivity. It's called as a relative permittivity or the dielectric constant. Another expression for the dielectric constant is that it is the ratio of the force between two charges in air to the force between the same two charges separated by the same distance in a medium. We can rewrite the given expression as follows. We can bring in the root epsilon r inside the bracket, and since we have 1 by 4 pi epsilon naught outside, it must be the force in air. So the distance in air becomes root epsilon r times r, which is the equivalent thickness of air. This is an important idea you need to know. Quickly moving on to another simple example. Two point charges q1 and q2 are separated by a given distance. If q1 is increased by 25% and q2 is decreased by 10% and the dielectric constant of the medium is increased by 50%, find the new force between them. Here's the solution. The force is F is equal to k q1 q2 by epsilon r squared, and when the quantities are changed, the new force turns out to be k 1.25 q1 and 0.9 q2 and 1.5 epsilon r. Solving, we get the new force to be 0.75 times the original force. Let's get on to the next idea. What is the expression for Coulomb's force in a partial dielectric? Now the force expression can be rewritten as the following. What we have done is that the 2 point charges q1 and q2 are now separated by a given distance r, but there is a partial dielectric of thickness t between them. So we have replaced this partial dielectric by air, which is root epsilon r times t, and then rewritten the entire formula for air as the medium between the two charges. Here r is the separation between the charges and t is the thickness of the dielectric. Let's solve an example based on this idea. 2 point charges exert a force F on each other when separated by a distance d. If a dielectric medium of thickness d by 2 and dielectric constant 9 is introduced between the charges, find the new force between the charges. Here's the solution. Initially the force is k q1 q2 by d squared. Now in a given medium, we replace the distance into the effective distance, which is d plus root of the dielectric constant, which is 9 minus 1, into thickness of the dielectric, which is d by 2. Of course, whole square of that. On solving, we get the final expression for the force in the medium to be force in air by 4. Now coming to the principle of superposition. The force on a given charge due to a system of charges is the vector sum of the forces due to the individual charges. That is, if you want to find out the force on a charge q due to a system of charges q1, q2 up to qn, then the force on the charge q is given by force on charge q1 plus force on charge q2 plus up to force on charge qn, and what kind of an addition is that? It is a vector addition. So this is the essence of the principle of superposition. Let's again get into an example. A charge q is placed at two opposite vertices of a square. if charges minus q are placed at the two other corners, find the net and the net force on q is 0. Find the relation between q and small q. And the net force on q is 0. Find the relation between the two charges. Here's the diagram. Charge q is at two opposite corners and charge minus q is at the other two corners. Now, if q is positive, then minus q will attract it, and these are the two forces F due to minus q, and since these two forces will be equal in magnitude, the resultant will be root 2F, which is along the diagonal. Since q is positive, the other q will repel it, and let the force between them be F prime. Now if the net force on capital Q should be 0, then these two forces must balance each other. So we have F prime must be equal to root 2 times F. We have kq square by a square is equal to k times capital Q small q by a square. And on solving, we get q is equal to minus 2 root 2 times q. That is, if minus q or q and q must have opposite signs. Coming to the final idea in this lecture, null point. So null point for a system of charges is that point in space where any other charge placed experiences zero force due to the system of charges. That is, if you want to find the null point due to a system of charges q1, q2 up to qn, place a charge q there, and the net force on q, which is given by the principle of superposition, should turn out to be 0. Then we call that point as the null point. Let's solve the example. Two charges plus q and minus 4q are placed at distance L apart. Find the null point and the third charge to be placed at that point, which keeps the system in equilibrium. Now how do we solve this? So q and minus 4q are placed at distance L apart. We have to place a third charge q prime such that the system of three charges remains at equilibrium. First, at P, wherein q prime is placed, the net force on q prime must be 0. So on finding the net force at q prime due to q and minus 4q, we have the following expression. Solving, we get x is equal to L. That means q prime should be placed to the left of q at a distance equal to L itself. Now this explains as to why q prime must be in equilibrium, but the net force on any other charge should also be 0 because the system should be in equilibrium. So net force on q should be 0. So on equating the two forces on q due to q prime and minus 4q, and using the fact that x is equal to L, we have q prime is equal to minus 4q. Why should q prime be negative? Is because minus 4q will attract q. So q prime should also attract q. That can happen only if q prime is negative. And its value must be minus 4q. And if this is the case, then the entire system will be in equilibrium. Thank you.